Hello, and welcome to our discussion of the Parseval and Plancherel identities. We'll start with two functions f and g from the interval minus p to p into the complex plane that are integrable. Then, Parseval's identity tells us the following. The integral from minus p to p of f of x times the complex conjugate of g of x is equal to 2p times the sum from k equals minus infinity to infinity of the Fourier coefficient f hat of k times the complex conjugate of the Fourier coefficient g hat of k. So let's look at both sides of this identity for a minute or two. If I have my functions f and g integrable on the interval minus p to p, then it's a fact of integration theory that their product, f times g conjugate, will also be integrable. So the existence of the integral on the left is not a problem. On the right, I have integrable functions f and g, so their complex Fourier coefficients f hat and g hat are both defined. So the terms of this doubly infinite series on the right are defined. But why on earth should this doubly infinite series converge in the synchronous sense that we've been using for doubly infinite series convergence? And if it does converge, why should it have anything to do with this integral relation? We've sort of gone from a continuous quantity, this integral of f times g conjugate, into an infinite sum of a bunch of discrete quantities, the product of f hat times conjugate of g hat. For better or for worse, the proof is something that comes out of the abstract Fourier material from Appendix C.5, which I'm not at all requiring you to read or look into. So it's there if you're curious, but we can just accept Parseval as a fact. One thing that's important if you're consulting other books is our factor of 2p. The integral is 2p times the sum. Depending on how people scale things with their Fourier series and Fourier coefficients, this 2p might appear in weird places. This is where it goes for us. Parseval can give us another identity, Plancherel. So if I have f integrable on minus p to p, then the square of its L2 norm exists, so that's equal to the integral from minus p to p of the modulus of f of x squared. And then I just rewrite the integrand a little. This is the integral from minus p to p of f of x times the complex conjugate of f. So I look at Parseval's identity, and I take f equal to g, and I get 2p times the sum from k equals minus infinity to infinity of f hat of k times conjugate of f hat of k. But of course, a complex number times its conjugate collapses into something simpler. This is 2p times the sum from k equals minus infinity to infinity of f hat of k modulus squared. So again, I've gone from representing a continuous integral on minus p to p as a multiple of a sum of discrete numbers f hat of k. And one way people like to use the Parseval and Plancherel identities is to evaluate integrals, or to evaluate sums, rather, that we couldn't quite evaluate from methods of calculus. So in this example, we'll look at the sum from k equals 1 to infinity of 1 over k squared, and we're going to show that this is equal to pi squared over 6. Now this sum from k equals 1 to infinity of 1 over k squared might look familiar to you from your calculus days. You could use the so-called p-test for series to show that this series converges. Or you could do a comparison test or a ratio test or something like that, and you would know that the sum from k equals 1 to infinity, 1 over k squared, converges. Great. What does it converge to? Most of our convergence tests from calculus, other than maybe the geometric series test, don't really tell us what the sum of the series is. They just say, yeah, it converges, and good luck finding the sum of it. Here we are actually going to find the sum of the series. And we do this by relating the series to a function on an appropriate interval, and then fooling around with that function's Fourier series and the Plancherel identity. This step is not obvious. What is the right function to introduce to relate this series to an integral? And often when I give you these problems, these are kind of toy problems, I will tell you what function you might want to use, and then leave it up to you to figure out the details of the connection. So one of our first, possibly the first Fourier examples that we ever calculated was the function f of x equals x. We know for this function that on any interval minus p to p, its complex Fourier coefficients are 0 for k equal to 0, and IP times minus 1 to the k over k pi for k non-zero. So I know I'm going to want to sum the squares of the Fourier coefficients, and for k not equal to 0, this IP times minus 1 to the k over k pi looks a lot like a constant multiple of 1 over k squared, or y squared. How more precisely can I get a 1 over k squared in here? Well, I have freedom to take p to be anything I want it to be. So let's take p equal to pi, and that'll kill off the pi in the denominator. So this tells me that if p equals pi, the square of the modulus of f hat of k is 0 for k equals 0, and 1 over k squared for k non-zero. Because in this expression for f hat, what's the modulus of I? 1. What's the modulus of minus 1 to the k? 1. So modulus squared of f hat of k is 1 over k squared for k non-zero. Great, this looks a lot like the terms in my series. So Plancherel tells me that the L2 norm of f squared is equal to 2 pi times the sum from k equals minus infinity to infinity of modulus f hat of k squared. Here p is equal to pi, so I have a factor of 2 pi in front of the sum. So what is this sum from k equals minus infinity to infinity of the modulus of f hat of k squared? Well, all my terms are 1 over k squared, except when k is equal to 0. So let me rewrite this as 2 pi times the sum from k equals minus infinity to infinity, excluding k equals 0, of 1 over k squared. Great. So this looks a lot like the series I started with, except now I'm summing over minus infinity to infinity, but at the start I only wanted to sum from 1 to infinity. Well, that's not too bad. I can just rewrite this sum from minus infinity to infinity excluding 0 as twice the sum from k equals 1 to infinity of 1 over k squared. Because you think I'm summing 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. In the negative direction, I'm summing 1 over minus 1 squared, 1 over minus 2 squared, 1 over minus 3 squared. So I just double the series and go from k equals 1 to infinity. This leads me to a 4 pi in front instead of a 2 pi. So what have I established by Plancherel and a little reindexing? That the L2 norm of f squared is 4 pi times the sum from k equals 1 to infinity of 1 over k squared. My original series was sum from k equals 1 to infinity of 1 over k squared. So all I have to do is get rid of that factor 4 pi and calculate the L2 norm of f squared, and I know what the series sums to. That is, sum k equals 1 to infinity of 1 over k squared is norm of f in L2 squared over 4 pi. So that's 1 over 4 pi times the integral from minus pi to pi of modulus f of x squared, because that's what the L2 norm is when you square it. And so this is 1 over 4 pi times the integral from minus pi to pi of x squared. So thanks to Plancherel and a little reindexing, my infinite series becomes an integral of a very familiar function. And so this integral turns into 1 over 4 pi, pi cubed over 3 minus pi cubed over 3, and this collapses to 1 over 4 pi, 2 pi cubed over 3, which is pi squared over 6. So we have evaluated our sum from k equals 1 to infinity, 1 over k squared, using Plancherel and some integrals, and that turns out to be pi squared over 6. A very familiar series from introductory calculus that we probably could not evaluate using calculus methods at all.